Languages, levels, and virtual machines. The problem can be attacked in two ways. Both involve designing a new set of instructions that is more convenient for people to use them. The set of built-in machine instruction. Taken together, these new instructions also form a language which we will call L1, just as the built-in machine instruction from a language which we will call L0. The two approaches differ in the way programs written in L1 are executed by the computer, which, after all, can only execute programs written in machine language L0. One method of executing a program written in L1 is first to replace each instruction in it by an equivalent sequence of instruction in L0. The resulting program consists entirely of L0 instruction. The computer then executes the new L0 program instead of old N1 program. This technique is called translation. The other technique is to write a program in L0, then takes program in L1 as input data and carries them out by examining each instruction in turn and executing the equivalent sequence of L0 instruction directly. This technique does not require first generating a new program in L0. It is called interpretation, and the program that carries it out is called an interpreter. Translation and interpretations are similar in both methods. The computer carries out instruction in L1 by executing equivalent sequence of instruction in L0. The difference is that the translation, the entire L1 program is first converted to an L0 program. The L1 program is thrown away and then the new L0 program is loaded into computer's memory and executed. During execution, new generated L0 program is running and in control of computer. In interpretation, after L1 instruction is examined and decoded, it is carried out immediately. No translated program is generated here. The interpreter is in control of computer. To it, the L1 program is just data. Both method and increasingly a combination of two are widely used. Rather than thinking in terms of translation and interpretation, it is often simple to imagine the existence of hypothetical computer or virtual machine whose machine language is L1. Let us call this virtual machine M1 and let us call the machine corresponding to L0 and M0. If such a machine could be constructed cheaply enough, there would be no need for having language L0 or a machine that executed programs in L0 at all. People could simply write their programs in L1 and have the computer execute them directly, even if virtual machine whose language is L1 is too expensive or complicated to construct out of electronic circuit. People can still write program for it. These programs can be either interpreted or translated by a program written in L0 that itself can be directly executed by existing computer. In other words, people can write programs for virtual machine just as though they really existed. To make translation or interpretation practical, the languages L0 and L1 must not be too different. This constant often means that L1, although better than L0, will still be far from ideal for most applications. This result is perhaps discovering in light of original purpose for creating L1, relieving the programmer of the burden of having to express algorithm in a language more suited to machines than people. However, the situation is not hopeless. The obvious approach is to invent still another set of instructions that is more people-oriented and less machine-oriented than L1. This third set also performs a language which we will call L2 and with virtual machine M2. People can write program in L2 just as though a virtual machine with L2 as its machine language really existed. Such programs can be either translated to L1 or executed by an interpreter written in L1. The invention of a whole series of languages, each one more convenient than its predecessor, can go on indefinitely until a suitable one is finally achieved. Each language uses its predecessor as a basis, so we may view a computer using this technique as a series of layers or levels, one on top of another as shown in the figure. The bottommost language or level is the simplest and topmost language or level is the most sophisticated. There is an important relationship between a language and a virtual machine. Each machine has machine language consisting of all instructions that the machine can execute. In effect, a machine defines a language. Similarly, a language defines a machine, namely the machine that can execute all programs written in the language. Of course, the machine defined by certain language may be enormously complicated and expensive to construct directly out of electronic circuit, but we can imagine it nevertheless. A machine with C or C++ or Java as its machine language would be complex indeed, but could be built using today's technology. There is a good reason, however, for not building such a computer. It would not be cost effective compared to other techniques. Merely being double is not good enough. A practical design must be cost effective as well. In certain sense, a computer with n levels can be regarded as n different virtual machines, each one of with a different machine language. We will use the term level and virtual machine interchangeably. However, please note that, like many terms in computer science, virtual machine has other meaning as well. We will look at another one of these later on the coming lectures. Only programs written in language 0 L0 can be directly carried out by the electronic circuits without the need of intervening translation or interpretation. Programs written in L1, L2 up to L1 must be either interpreted by an interpreter running on lower level or translated to another language corresponding to a lower level. A person who writes programs for the level and virtual machine need not be aware of underlying interpreter and translator. The machine structure ensures that these programs will somehow be executed. It is of no real interest whether they are carried out step by step by an interpreter, which in turn is also carried out by another interpreter, or whether they are carried out by the electronic circuit directly. The same result appears in both cases. The programs are executed. Most programmers using an n-level machine are interested only in the top level, the one least resembling the machine language at very bottom. However, people interested in understanding how a computer really works must study all the levels. People who design new computers or new levels must also be familiar with levels other than the top one. The concept and technique of constructing machines as a series of levels and details of levels themselves form the main